what ways do the brain and the computer fundamentally differ in how they compute logic and how they compute signals, how they compute functions, anything? What are the biggest ways for an average listener where might have a misconception about how the brain is related to the computer or computer is related to the brain? How do they fundamentally differ?
So this is a deep hole for most theoretical neuroscientists. So it depends on the definition of computer. So the computer that's sat in front of me now is a keyboard, screen, it has a hard drive, it has a processor, it has a memory in it, so on. So when you say computer, it most often invokes that kind of architecture, something which has got a processor in it, has got a memory in it, it's got some kind of interface system. So whether it be my phone, this laptop, a tablet, a really smart fridge, that's the way that we think of computers when we say computer. From that perspective, it's very easy. The brain is that case not that kind of computer. Right? We don't have a separate memory store from a separate computational store. And then there's the more complex version, which is a computer is, if you say a computer is sort of Alan Turing or the George Church type approach, where we say a computer is anything that can run an algorithm, then the brain is a computer because it can run pretty much any algorithm. But in that case, a rock is an algorithm because it runs some physics algorithms. It runs falling down when it's released. Right? So in that sense, the brain is trivially a computer, but not interestingly a computer. So somewhere in between is the interesting question of if I commit myself to a particular model of how a computer works. So, for example, if I say I really want to commit to the idea that the brain works by say, let's start with you mentioned logic. So brain works by having a series of statements of logic, which is the same as we meant inside our laptops or our phones in the processor, where you have a series of transistors which are either on or off, so everything is in this binary logic form. Then the sense in which it's the same is the sense in which, yes, neurons have this binary output, this 0 and 1, this spike. That much lines up. And indeed, historically, that's what inspired von Neumann when he designed the original sort of what's now the architecture that we use for everything with separate processor and memory and the way it's controlled, the buses and so on. He was inspired by Kullak and Pitt's work on the neurons and logic and the fact that we want something that has a 0 and 1 because that will work really cool. Hence, we have a system that's based on this 0-1 idea. But as we just noted, it's very easy to find ways in which the brain doesn't work in this simple binary logic way, in which you have a lot of particularly the work of the neurons towards the periphery, where they're controlling the muscles, or the input they get from, say, the senses, isn't done by logic, but it's done by transducing this information into some kind of analog signal that is used by neurons further in.
So what about artificial neural nets versus brain neural networks then? What are the main things that those systems do that are the same? And then what are some of the fundamental differences? Because, neural networks are all the rage at the moment. People talk about the large language model development in the last year or two has been an absolute explosion. I think people have this word neural network in their head and they sort of understand that's how neurons work in the brain. And that's also how ChatGPT works in large language models. What are some of the parallels? What are the similarities? And then what are the big crucial differences, if there are any?
I guess the main similarity is that, at heart, in an artificial neural network, you've got a whole series of units, and those units they receive input from a bunch of other artificial neural units. They sum them up and they give some kind of output as a response. That's the fundamental operation in any artificial neural network, and that is a true, if crude, cartoon of how actual neurons work. So yes, neurons get their inputs, they summate them, and they turn them into some kind of output signal. So this kind of spikes. I mean, the principal difference is that pretty much any artificial neural network you hear about or read about, of course, the output is just a continuous signal. So all these inputs, these units are getting, their outputs they're giving, they're all continuous in some way. Often they're bound between 0 and 1, but in that range they are continuous. Whereas, obviously, what a neuron sends out is a spike. So the only way that they are the way they translate as being the same is that is only if we have a scheme where we count the spikes and say, all right, so if a neuron can send out something between 0 and say 100 spikes, and it's currently sending out 5 in this second, or maybe it's sending out 10, maybe it's sending out 20, then you have this continuous range of the number of spikes. But there's good reason to believe that a whole lot of processing in the brain doesn't work by counting of spikes, because often there just simply isn't enough time to do that. So, so there's some nice famous experiments where they're flashing an image up on the screen and looking for the earliest detectable response to the image on screen inside the prefrontal cortex. And the earliest detectable response happens within about 100 or so milliseconds. So 100 or so milliseconds, most neurons in the long chain from the eyeball through the various connections in the brain from the visual cortex all the way back all the way to the front, most of them haven't had a chance to send a single spike, let alone multiple spikes.
Yeah.
So however that information is going to the front, it's not because every neuron is waiting in turn for saying, oh, I've just received 20 spikes, I'm now going to send 10, go down, because that would take forever. So there's a clear reason why a fundamental question really actually in neuroscience is, why does the brain use spikes and not something else?
Yeah.
Given that, we can happily design artificial systems which don't need them. So artificial neural networks can do really cool stuff but don't need them. So it's an open question as to whether the reason the brain uses spikes is because of some fundamental biological reason. So for example, that to send information biologically over long distances, you need a system where you can just send a pulse that is reliable, that you can regenerate, that will travel a long way, because sending a continuous signal will dissipate, it will fall apart, you'll get lost in noise very quickly. Or whether there's a fundamental computational advantage to having the spikes, in which case, whatever that is, that's missing from artificial neural networks.
So that difference really isn't quite known just yet of why it's using a discrete signal versus a continuous signal, and what the benefits might be of that specific spike. Because the brain does seem to be, and you touch on this in the book as well, it's far more energy efficient than any artificial neural network, right? Magnitudes more energy efficient. Could that be because it's processing a discrete signal versus something that's maybe bulkier, which is a continuous one?
Yes, and certainly that. So yes, although of numerous reasons why it could be using spikes, the energy efficiency argument is a really strong one. And that's indeed the argument underpinning why so many of the big chip companies are trying to develop neuromorphic chips, where the processing on board is essentially spiking neurons as opposed to transistors. Because you can then, in those chips, in theory, do a lot of similar computational work, but vastly lower expense than if you're doing this continuously updating thing, essentially because it's an event-driven system that you only ever bother updating when a spike turns up.
Explain that a little bit more. How are these neurons existing? What is a neuromorphic chip? How are these neurons existing on some sort of motherboard or something? Explain that a little bit more.
So in the ones that I know best, they essentially build into hardware a particular model of a neuron. So there's a particular class of model neurons I work on quite a lot, that some neuromorphic chips embed directly into them, essentially create layer upon layer of these types of neurons. And then I guess we're back to the logic. They end up being able to obviously use them to be able to do traditional computational operations on them, but now simply by passing spikes rather than having millions or billions of transistors doing the same job. So there's still a lot of money being pumped into these things. They've been going for neuromorphic chips, a good 15 years, probably 20 years now. And are still big announcements every now and then from, say, IBM or Qualcomm, and saying, look, we got this amazing new chip that can do all this new stuff. But yeah, it's still not clear to me how much further they need to go forward in order to be usable, whether we actually cracked the energy efficiency barrier.
Gotcha. Explain. Let me know if I have any of this wrong, but it's my understanding as well that one of the crucial differences between the artificial neural networks and the neural networks in our brain is that backpropagation is a very important process in which the output of an artificial neural network is fed back in the layers and adjusts the layers. But there isn't any backpropagation process in the brain. The electronic flow goes through the axon in one direction and doesn't flow backwards. Is that accurate?
Yes and no. So you're right. So obviously the way that backprop works in artificial neural network, it's done so in a way that it's very hard to conceive of how you would do that biologically. Essentially, because in the way that that's done, obviously that's, as you say, that's taking sort of the output of one layer, setting it back up to the layers behind it to essentially tell them where the error was in what its output was. And to do that, it needs to know something about the change of the weights that happen behind it. So it has to transmit backwards information that you couldn't possibly know in biologically speaking. Having said that, there are mechanisms by which neurons communicate to the neurons behind them.
Uh-huh.
So when a neuron, some particular types of neuron, not all neurons, but when some types of neurons, like the pyramidal cell, when they send a spike along their axon, because that is initiated right at the edge of the neuron's body, that also there is a similar depolarization of the membrane that gets propagated back up, so it gets sent back up into the dendrites. So there is a sweeping back electrical signal, and there's a lot of speculation, a lot of work on how that might drive, maybe a signal for driving changes of the strength of connections between neurons. So
Gotcha.
that when that signal goes back up, essentially the signal to the rest of the neurons saying, I have just sent a message. If I have received something interesting just before that, maybe it's worth changing one of those synapses. And there is a whole little sort of cottage industry of theorists who have been trying to work out ways of making something like a backprop work plausibly in neural tissue. So so there's a bunch of schemes for making something that looks like something has to know about the change in weights in the layers behind it work. Some which are more plausible than others, but yes, it's an area where people feel like, okay, so it's not entirely impossible that a brain could do something like this, but clearly not in the exact mathematical way that backprop works.
Gotcha. That's great. That's updated my understanding, because I wasn't sure that there was any resultant feedback structure that sort of resembled in some way that backpropagation. So that's very interesting.
I hope you enjoyed that clip with the amazing Dr. Mark Humphreys, computational